Welcome. What you're looking at is the title of a story that is still being written, and it may turn out to be the most consequential economic story of our lifetimes. We're going to spend the next hour or so exploring the economics and infrastructure of what many are calling the AI supercycle. And I want to be clear from the start, this is not a presentation about AI in the abstract. This isn't about chatbots or creativity or whether AI will write your emails. That's the surface layer. What we are here to talk about is the physical, financial, and geopolitical machinery underneath all of that. We're talking about compute, raw, brute force computing power. We're talking about power grids and gigawatts of electricity. We are talking about a tiny number of companies and machines that the entire global AI revolution runs through. And we are talking about where the money flows and where it doesn't. By the time we are done, you'll have a sharper mental model of understanding why headlines about AI look the way they do, why chips are treated like strategic weapons, why tech companies are buying nuclear power plants, and why the race to build AI infrastructure may reshape the global economy as fundamentally as railroad did in the 19th century or the internet did in the 20th. Let's get into it. Before we dive in, let me map out what we are covering today. We have 7 sections and they build on each other deliberately. We start with the compute revenue link, a deceptively simple observation that turns out to explain almost everything about how AI industry works financially right now. From there, we go into the scaling laws, the technical rules that govern AI improvement and explain why the conventional wisdom about how those laws work has been completely overturned. Third, we look at agentic AI, the shift from AI that answers questions to AI that actually does things. This changes the infrastructure requirements dramatically. Then we'll spend real time on power and physical infrastructure because the energy problem is genuinely one of the most under-discussed constraints in the industry. From there, supply chain risks, which is where the story gets geopolitically interesting. Then the latency war, because speed isn't just a nice to have, it's a competitive survival issue. And finally, we look forward at where value is going to accrue over the next 5 years and what that means practically. Compute is the new capital. In the industrial age, if you wanted to build a dominant business, you needed factories and machinery. Capital meant physical capacity to produce things. In the internet age, the formula changed. The companies that won were sitting on mountains of data. Data became the new oil, we were told. Today, in the age of frontier AI, neither of these is the scarce resource. The scarce resource is compute, raw processing power. And this isn't just poetic framing, it's measurable and literal. Here's the key fact to hold on to. For the leading AI labs, revenue is a lagging indicator of compute capacity, not the other way around. They don't build compute to meet revenue, revenue follows compute. The pattern is astonishing. Compute tripled year over year, revenue tripled, compute tripled again, revenue tripled again. 3 years in a row, no exceptions, no ceiling hit. And notice that third stat on the screen, the number of times we observed a point of diminishing returns, where more compute failed to produce more revenue. That number is 0. That means the single most important strategic questions for these organizations isn't what's demand like, it's how much compute can we get our hands on. Let's put some numbers on this. The chart on the left shows what happens when you index compute capacity and revenue from 2022 and trace them forward. The shape is nearly identical. Compute goes up, revenue follows. The compound rate of tripling annually isn't just fast, it's historically unprecedented. To put it in the context, Moore's law, the famous observation that transistor density doubles roughly every 18 months, was considered one of the most relentless growth curves in economic history. AI compute at the frontier is growing faster. Now, on the right side of this slide, I want to highlight 3 concepts that explain why this relationship holds. First, Moore's law versus AI law. Moore's law was about the hardware getting better. What happened now is that more hardware is being deployed year after year at a pace that outstrips even Moore's improvements. Second, token economics. The operational goal of every AI infrastructure team is threefold. make each computational unit or token cheaper to produce, make each token more intelligent, and reduce the number of tokens needed to complete any given task. All three simultaneously. That is the engineering challenge behind the revenue machine. Third, and perhaps the most striking, as of right now, no ceiling has been detected. Nobody has found the point where more compute stops paying off. That's either thrilling or alarming depending on your perspective, but it is the reality. I want to emphasize on this again. Compute capacity is the ultimate leading indicator for revenue. In the traditional software world, revenue was driven by sales cycles and user acquisition. In the AI supercycle, the formula has become much simpler. Revenue is equal to total compute into utilization. Revenue is equal to total compute into utilization rate. For frontier labs, revenue is actually a lagging indicator of how much compute they have managed to operationalize. Over the last 3 years, we have seen a remarkable correlation. Compute capacity has tripled year over year, and revenue has followed the exact trajectory. This 3x year over year increase shows no sign of slowing down. There is currently no visible end to the correlation between expanding capacity and corresponding market demand. If you build the compute, the market will consume the tokens. The mission, therefore, is threefold: make tokens cheaper, make every token more intelligent, and reduce the number of tokens required to complete a task. We push on these three dimensions simultaneously. We improve hardware and software to generate tokens more cheaply, push model capabilities so every token carries more reasoning weight, and use tools like Codex to ensure tasks require less chatter to reach a result. This creates a recursive economic engine. As tokens become cheaper and smarter, they're integrated into more complex workflows, shifting from simple coding to general purpose knowledge work. This drives further demand for compute, which justifies further capital expenditure. As long as we can maintain high utilization rates, the constraint on companies' top line revenue is no longer product market fit in the traditional sense, but the physical ability to stand up gigawatts of compute. Beyond pre-training, now let's go one level deeper into the technical landscape. For years, when people talked about AI and compute, they were almost exclusively talking about training, the process of feeding an AI model massive amounts of data until it learns patterns and develops capabilities. And the conventional wisdom was that scaling laws, the rules governing how AI improves with more compute, applied mainly to the training phase. That view is now obsolete. Look at the pipeline on the slide. When AI was young, all the compute focus was on pre-training. That was one lever that seemed to matter. But over the last few years, the frontier has expanded dramatically in both the directions. Post-training now includes techniques like reinforcement learning from human feedback, where models are refined through millions of evaluations after the initial training is complete. Then we have the inference, the act of actually running the model to generate outputs. And finally, we have agentic loops, where models are running continuously, calling on themselves and other tools to complete complex tasks. A landmark study from DeepMind, the Chinchilla paper in 2022, showed that the optimal way to train a model requires careful balancing the size of the model against the volume of data it's trained on. That was a turning point. Since then, researchers and engineers have found the same principle of more compute equals better results extends well beyond training into every phase of model's lifecycle. The compute demand didn't just grow, it exploded across every dimension. The inference explosion, the headline stat on the slide is on that still surprises most people when they hear it for the first time. Inference is projected to account for more than 80% of all AI compute. Let me make sure that lands properly. We've been talking about training, the big expensive thing AI companies do to create a model. But running that model, serving it to users, using it inside products, that's inference. And inference is going to dwarf training in terms of raw compute consumption. Why? 3 reasons shown on the right. First, reinforcement learning. Once a model is trained, the work doesn't stop. Post-training refinement through reinforcement learning, where models essentially learn from evaluating millions of their own outputs, is itself an inference-heavy process. Every evaluation is an inference call. Second, synthetic data generation. Here's a subtle and important problem. The world is running out of high quality human generated text and data to train new models on. We have essentially scraped the internet now, so now models generate their own training data, which requires running the model, which is inference. Third, reasoning models. The thinking AI systems, the one that pauses and work through a problem step by step before answering, require multiple sequential inference calls to produce a single response. Every step of that thinking process is a compute event. Add this up and you see why infrastructure teams are increasingly focused not on training clusters but on inference infrastructure. The demand is going there. From chatbots to agents, this slide represents one of the most important transitions happening in AI right now, and it has profound implications for the infrastructure that supports it. The left side of this slide shows you the old model, a chatbot. You send a message, the AI responds. One interaction, one inference call. The GPU handles it, the response comes back, the session ends. It's essentially stateless. The system doesn't remember you or carry anything forward between conversations. Simple, effective, and relatively easy to engineer. Now, look at the right side, an agent. This is an AI that doesn't just respond to you, it acts on your behalf. An agent takes a goal, say research these 5 companies and prepare a competitive analysis, and it executes a multi-step plan to accomplish it. It calls external tools, it queries databases, it searches the web, it might spin up a virtual machine to run code, it maintains memory across all of those steps so it doesn't lose context. Each of those actions is a compute event. Many of them involve inference calls. The overall structure isn't a single GPU pass, it's a branching, parallel orchestrated graph of computation. This is architecturally a completely different beast, and it means the infrastructure underneath needs to be fundamentally different too. You cannot run a sophisticated agent economically on a GPU cluster alone. You need a heterogeneous mix of processing units, which is exactly what we're going to explore next. The agent compute graph. Agents require a DAG, directed acyclic graph of heterogeneous compute, not a single GPU pass. As we move into the agentic era, we have to move beyond a single node. A simple chatbot requires one-to-one compute graph, but an agent requires a dynamic branching pathway, a directed acyclic graph or DAG. Look at the complexity mapped out on this slide. A single user prompt no longer triggers just one inference call. It might trigger an initial inference call, which then decides it needs more information and makes a tool call or a database search query. That data is fed back into another inference call, which might then decide to spin up a VM environment to test some code it has written. If the test fails, the model performs self-correction, looping back to a previous node to try a different approach. This creates what we call the infrastructure mandate. This complex execution graph requires an intelligent distribution of compute. You cannot run this entire graph entirely on a single type of hardware. You need to route specific tasks dynamically to the most efficient hardware node. For example, search query node has different compute requirements than a reasoning inference node on a VM test node. Orchestrating this DAG in real time ensures that data flows between these nodes with minimal latency while maximizing the utilization of specialized hardware. And this is the core challenge of modern AI infrastructure. This is why compute is no longer just about chips. It's about the orchestration software that manages the complexity to deliver a final executed outcome. Now let's go to section 4, power and physical infrastructure, the gigawatt problem. Let's talk about power, because you've been following the AI industry and wondering why tech companies are suddenly talking about nuclear reactors and building their own power plants. This slide is where that story starts. Look at the 3 numbers at the top. 100 gigawatts. That is approximate compute capacity being planned by the US hyperscalers. That is the big cloud providers building the infrastructure that AI runs on. 100 gigawatts. Now, look at the middle, that is 30 gigawatts. That is the aspirational power target of a single AI lab, more than 10%. That is the projected share of total US energy consumption that AI will represent in the not too distant future. To put 100 gigawatts in context, the entire current US electrical grid produces around 1000 gigawatts at peak. AI data centers are planning to consume a tenth of that, and this is demand that didn't meaningfully exist 5 years ago. This creates three serious problems shown at the bottom of this slide. Grid instability. Modern AI training jobs are synchronized at massive scale, hundreds of GPUs and thousands of servers all doing the same thing at the same time. When a training run starts or stops, it can spike or drop the demand on the local grid by hundreds of megawatts instantly. Current power grids aren't designed to handle swings like that. Grid decoupling. The solution being pursued right now is to take the data centers off the public grid entirely and power them with on site generation, currently natural gas and increasingly nuclear, and thermal sensitivity. Today's AI chips are extraordinarily fragile when it comes to power and cooling consistency. Any fluctuation causes them to throttle back performance. Stable power isn't just an environmental concern, it's a performance critical requirement. To understand the scale of industrialization of intelligence, we have to look at the numbers. We have moved past the era of server rooms and even data centers as they were traditionally understood. We are now talking about target ambition 30 gigawatts. Let's break down the unit economics of this scale. A single high-end GPU consumes between 1 and 2 kilowatts. A standard data center might handle 50 megawatts, but a single gigawatt facility, which represents roughly half a million GPUs, requires approximately $70 billion in capital expenditure. This is massive concentration of capital and physical infrastructure. When you aggregate the ambitions of all US hyperscalers, the goal reaches roughly to 100 gigawatts. To put that in perspective, 100 gigawatts represent double-digit percentage of the entire US electrical grid capacity. This shift means that energy is no longer just for human consumption, it's becoming a primary industrial input for the production of intelligence. This level of ambition demands national scale orchestration. You cannot simply plug a 1 gigawatt facility into a local substation. So, sourcing this much compute means securing the entire supply chain: chips, memory, networking, cooling, data center buildings, power generation, and land. It's a fist fight for resources. Furthermore, building at this scale is an operational nightmare. A 1 gigawatt facility scaling up its compute in unison can trigger 100 megawatt fluctuations on the local grid in seconds. If not engineered perfectly, these facilities risk causing statewide blackouts. This is why we are seeing a push towards decoupling from the grid and moving towards natural gas and eventually nuclear power. Power availability has quietly become the single most important constraint on AI expansion. Not talent, not capital, not even chips. Power. The bar chart on the left tells the story of how fast this has escalated. Total US data center power consumption stood at around 17 gigawatts in 2020. By 2024, AI specific data centers had pushed that to roughly 40 gigawatts. The planned capacity from hyperscalers alone pushes past 100. And by 2030, AI could represent a double-digit percentage of total US energy consumption. Now let's look at the energy sources shown on the right, because this is where strategy meets physics. Solar and wind are growing fast, but they are intermittent. The sun doesn't shine and the wind doesn't blow, then your data center goes dark. When the sun doesn't shine and the wind doesn't blow, your data center goes dark. That's not acceptable for 24/7 compute operations. And the battery storage required to buffer that intermittency at gigawatt scale doesn't exist yet. Natural gas is the current bridge solution. Multiple large AI operations are already building on-site natural gas turbines, not connecting to the grid at all, but generating their own power. Nuclear is the future that the industry is clearly betting on. Several AI companies have made headlines for pursuing power purchase agreements with nuclear plants, and some have gone further, actively trying to restart dormant nuclear facilities. Nuclear provides stable, dense, carbon free, baseload power that large data centers need. Grid storage, large battery buffer systems is emerging as complementary tool, helping to smooth out demand spikes during synchronized training runs even when the grid connection exists. The energy problem is real and it is now shaping AI strategy as much as any technical consideration. There is common debate in infrastructure: should compute be decentralized in giant clusters or distributed at the edge, closer to the user? For the AI supercycle, the answer is clear. Centralized GW clusters currently outweigh edge distribution. There are three primary reasons for this. First, labor bottlenecks. The United States currently lacks the critical mass of specialized human labor required to build and maintain highly distributed infrastructure. It is far more efficient to concentrate the best engineering teams on massive 1 gigawatt builds than to spread them across hundreds of smaller sites. Second, per megawatt economics. Building a 50 megawatt data center is vastly more expensive on a per unit basis than building a single gigawatt facility. The economics of scale and power, procurement, cooling infrastructure, and physical security are overwhelming at the gigawatt level. Third, latency reality. There's a misconception that network proximity to the user solves the core latency bottleneck. In AI, the dominant latency doesn't come from the network, it comes from the pre-fill phase of the model itself. As we will see in the next slide, saving 20 milliseconds by putting a server in a local city is currently irrelevant when the model takes 400 milliseconds just to think before it generates its first token. Until we can distill highly intelligent models down to a size that can run locally, the economics and physics dictate massive centralized hubs of intelligence. We have talked about the demand side of AI infrastructure, the compute requirements, the power demands. Now let's talk about the supply side. And the picture here is genuinely concerning. The table on this slide maps the major components of AI infrastructure against their key players and risk levels. Let me take you through it. Logic and memory fabrication. The factories that actually manufacture chips is dominated by three companies: TSMC, Samsung, and Intel. That's it. The entire global semiconductor supply chain for cutting edge chips flows through these three facilities in three countries. The risk level is critical. Lithography equipment. This is where it gets extreme. To manufacture leading edge chips, you need a specific type of machine called EUV lithography system. Uh, There is exactly one company in the world that builds these machines, ASML, a Dutch company. The risk level here isn't just critical, it's extreme. We'll go deeper on this in the next slide. HBM memory, the high bandwidth memory that AI chips need to work with massive models, is supply constrained. SK, Hinks, Micron, and Samsung are the key players, and demand has consistently outpaced supply. AI accelerators. GPUs primarily are dominated by NVIDIA, with AMD as a distant second. Demand continues to dramatically outpace supply, with lead times stretching months. Finally, power infrastructure. The electrical engineering expertise needed to build and operate gigawatt scale facilities is dwindling. There's been underinvestment in this workforce for decades, and now it's becoming a bottleneck. This is a supply chain that is single threaded on a very small number of organizations. The systemic risk is substantial. I want to spend a little more time on the supply chain risk that is very critical. A moment on ASML specifically, because the story of this company is one of the most extraordinary in modern industrial history, and almost nobody outside of the chip company knows it. ASML is a Dutch company and headquartered in Eindhoven. They make a machine called EUV lithography system. EUV stands for extreme ultraviolet. This machine uses light at a wavelength of 13.5 nanometers, so short that it can only travel in a vacuum because it's absorbed by air, to etch circuit patterns onto silicon wafers at resolution so fine they are measured in atoms. Without this machine, it is it is physically impossible to manufacture the chips that power modern AI. The NVIDIA H100, the Apple M series, the AMD MI300, all of them require EUV, and ASML is the only company on earth that makes it. A single EUV machine costs approximately $380 million. ASML ships roughly 60 of them per year. The technology took more than 30 years and billions of euros to develop, and critically, building a competitor would take a minimum a decade or likely longer and would require breakthroughs in optics, vacuum engineering, and precision manufacturing that no other organization has yet achieved. This makes ASML one of the most strategically significant choke points in the global economy. Governments know it. The US has pressured the Dutch government to restrict ASML's ability to sell to China. Taiwan's security is partly a semiconductor security story, and anyone building an AI strategy that depends on continued access to cutting edge chips is, whether they know it or not, depending on one building in Netherlands. The entire $1 trillion AI supercycle, all the software, all the models, all the 30 gigawatt ambitions is currently suspended on a hyper concentrated manufacturing base. While capital is abundant, physical reality is inelastic. You can secure the 70 billion for a 1 gigawatt data center, but you cannot buy your way past the waitlist for lithography hardware. The funnel of the AI world narrows down to a single absolute choke point: ASML lithography machines. Every logic and memory fab in the world, whether it's TSMC, Samsung, Intel, or Micron, requires ASML machines to produce the next generation of chips. If ASML cannot produce machines fast enough, the entire supercycle slows down, regardless of how much money Google or Amazon wants to spend. This creates a high pressure environment where time to compute becomes more important than the amount of compute. The goal is to ensure that every other part of the supply chain, the land, the labor, the power grid, is ready and waiting the moment the chips come off the line. We are in a race against inelastic physical manufacturing, and the winners will be those who can most efficiently orchestrate their way through this funnel. Speed is the product, section 06, the latency war. Let's shift gears from supply chains to user experience, because there's a technical arms race happening at the product level that most people never think about. Latency, response time. The gap between when you submit a question and when the first word of answer appears on your screen. This is now one of the most intensely competitive metrics in AI. The current state, shown at the top of this slide, time to first token, the industry term for how quickly a model starts responding, is running at 400 to 500 milliseconds. Half a second, that doesn't sound like much, but in digital experience terms, it's an eternity. Human reaction time begins to notice delays about 100 milliseconds. About 300 milliseconds, frustration builds. About 500, user starts to disengage. Now look at the context figure. 400,000 tokens. That is the size of input context some models are being asked to process before they can respond. 400,000 tokens is roughly 300,000 words or several full-length novels. And before generating a single word of output, the model has to read all of that. This is called the pre-fill problem. The model must load and process its entire context window through an attention mechanism before producing any output. And that process is currently the dominant source of latency, dwarfing even the network time it takes to transmit the request. The consequence: companies looking to deploy AI at the edge, closer to the users on local devices, haven't gained the advantage they expected. Because the network latency they had eliminated is 20 or 30 milliseconds, but the model internal prefill latency is 10 to 20 times larger. The math doesn't yet favor edge deployment for large models. The target shown on the right, under 100 milliseconds, getting there is one of the defining technical challenges of this era. Anatomy of a metric, deconstructing the 500 millisecond time to first token. To understand why edge compute isn't the answer yet. We have to deconstruct the time to first token. When you press enter on the prompt, there's a delay of roughly 500 milliseconds before you see the first character of the response. Where does that time go? Roughly 10 seconds of tenths of milliseconds are spent on app routing, tokenization, and load balancing. But the vast majority, the 400 milliseconds, is consumed by the prefill bottleneck. Before a model can generate a single token, it must run the entire context window through its attention mechanism. Imagine you're using a tool like Codex on massive GitHub code base. The model might have a 400k token context window. It has to page through all the 400 tokens, hundreds of megabytes of data to compute the attention weights before it can generate the very first output token. This is a massive computational task that happens before you see anything on your screen. This is what we call the edge fallacy. If the prefill phase consumes 400 milliseconds, saving 20 milliseconds by putting servers geographically closer to the user is a marginal gain that doesn't change the user experience. So the focus for reducing latency isn't on moving servers, it's optimizing the prefill phase through better memory and architecture and specialized accelerators that can process massive contexts faster. A whack-a-mole problem of system optimization. Optimization in the AI supercycle is a whack-a-mole problem. Because the stack is so deep, from the memory base to the app layer, solving bottleneck in one area immediately exposes a new one elsewhere. We saw this clearly in what we call the Cerebras effect. By introducing highly specialized accelerators like Cerebras, we drastically reduced token generation latency at the silicon level. But the moment the silicon bottleneck was solved, it exposed the rest of the stack as a new limiting factor. Suddenly, the surrounding API and the application infrastructures, which were designed for slower GPUs, couldn't keep pace. We found that our own API infrastructure was adding more latency than actual compute. This forced us to do a massive round of software engineering to shave off tenths of milliseconds across every single layer, from how we handle load balancing to how we stream tokens to the user. And this is a relentless cycle. Every 30 to 50 milliseconds of shaved latency drives massive gains in user engagement and retention. As human attention spans continues to shrink, speed becomes a primary dimension of competition. But to achieve that speed, we cannot just buy faster chips. We have to relentlessly optimize the entire vertical stack. We have established that agentic AI requires heterogeneous compute and the latency is a core competitive metric. This slide shows you what the hardware landscape actually looks like and what each component contributes. GPUs, graphics processing units, are still the workhorse. They're optimized for the kind of massively parallel floating point arithmetic that large neural networks require. Training, batch inference, and core mathematics of AI model lives here. They represent roughly 55% of the compute footprint in a modern AI infrastructure setup. CPUs, central processing units, might seem like a legacy technology in this conversation, but they are actually experiencing a renaissance. As agentic AI grows, the work of orchestrating complex multi-step workflows, managing tool calls, handling API integrations, and maintaining state across long interactions is fundamentally sequential and logic heavy, precisely what CPUs excel at. And CPUs account for about 20% of the compute picture. ASICs, application-specific integrated circuits, are custom chips designed for specific tasks. Companies like Cerebras, Grok, and increasingly the hyperscalers themselves are building ASICs tuned for low latency inference or long context memory management. When you need to do one thing extremely fast and at extreme scale, a general purpose chip will never match a purpose-built one. Now, ASICs account for around 18% of the hardware mix. And then there's memory, specifically high bandwidth memory or HBM, which is the often overlooked bandwidth layer. AI models are enormous, moving model weights, activations, and context in and out of compute units fast enough to keep everything running efficiently requires memory bandwidth and standard DRAM. Memory bandwidth that standard DRAM simply cannot provide. This is the actual infrastructure stack, not the GPUs. GPUs plus CPU plus ASIC plus memory all working together. AI designing its own successors. Section '07 Future Outlook. The traditional chip design cycle runs over 3 years. You assemble a team of engineers, they design a new chip architecture, they simulate it, validate it, tape it out, send it to a fab, wait for silicon to come back, test it, find bugs, iterate. 3 years minimum, sometimes longer. That cycle is now being compressed in a way that would have seemed like science fiction 5 years ago. AI is being used to design the next generation of AI hardware. Look at the loop on this slide. You train an AI model, the model, having learned from vast libraries of chip design literature and engineering data, can now contribute to the design of the next chip. It can also generate and optimize the low-level firmware and software that runs on the chip. The faster chip is then deployed, enabling faster training of an even better model, which designs the even better chip. This is a recursive loop, and it's not theoretical. It's actively underway at several of the major AI labs and chip companies. The implications are significant. If traditional chip design takes 3 years and AI assisted design compresses that to 12 months or less, the pace of hardware improvement accelerates dramatically. The gap between the current best in class AI hardware and what comes next shrinks. And the advantage of having AI help design your next AI becomes compounding. This is one of the dynamics that makes AI supercycle feel genuinely different from the previous technology waves. The technology is participating in its own acceleration. Where does the money go? This slide is about a shift in the economic gravity of the AI industry, and it mirrors patterns we have seen twice before in the history of technology. Look at the numbers for 2025. Today, roughly 75% of value creation in AI is concentrated at the infrastructure layer, the chips, the power infrastructure, the data centers, the networking. Companies like NVIDIA have been the massive financial winners of the first phase of the supercycle. This is the gold rush era, and NVIDIA is selling the picks and shovels. Model providers, the frontier AI labs, capture around 20%. Platform developers, APIs represent just 4%. And applications, the actual software products and services that end users interact with, about 1%. Now, look at the 2030 projections. Infrastructure share drops from 75% to 30%, not because the infrastructure becomes less important, but because value has migrated up the stack. Platforms and APIs grow from 4% to 25%. Applications grow from 1% to 20%. We have seen this movie before in the mobile revolution. The initial hardware manufacturers, makers of physical phones, captured enormous value in the early years. Then the value shifted to operating systems, then to app stores, and then to apps themselves. Companies that existed purely as hardware vendors often got displaced. In the cloud revolution, the early winners were the infrastructure layer, data center builders, server manufacturers, then AWS, the SaaS platforms, then cloud native applications. The analogy isn't perfect, but the directional dynamic is clear. Value migrates up the stack over time. The question every organization should be asking is, where in the stack do you want to be positioned in 5 years? This might be the most provocative question. Will traditional apps survive? And I want to address it honestly rather than hyperbolically. The app model shown on the left is how we have organized software for the last 15 years. You have a specific need, you go to the app store or the browser, you find an app, you learn its interface, you work with its constraints. You have data living in that app's silo. You are the orchestrator. You are the one switching between the apps, copying and pasting between the tools, assembling the workflow manually. The agent model on the right inverts this. You state a goal in a plain language. The agent, the AI, selects the tools it needs, calls them, manages the workflow, integrates the results. The interface becomes, in some cases, literally invisible. There's no UI to learn because there's simply no UI. There's just an outcome. Now, I want to be careful here. I'm not predicting that apps will disappear tomorrow. Many applications will persist because they provide value beyond pure workflow orchestration. Creative tools, complex professional environments, social platforms, those have intrinsic interface value. But for the large class of productivity software, tools whose primary function is to help users get information, move data between systems, generate context, or complete repeatable processes, the agent model represents a genuine existential question. If an AI agent can accomplish the outcome directly, why navigate to a dedicated application at all? The app as a user interface paradigm may increasingly become a crutch, a legacy construct from an era where humans had to manually orchestrate digital workflows because machines couldn't. Unexpected comebacks, the CPU renaissance. I want to spend a moment on something that doesn't get nearly enough attention in AI coverage. The unexpected revival of some older technologies and domestic manufacturers that may have had written off. The first unexpected comeback is the CPU, the central processing unit. The classic general purpose chip that has powered personal computers since the beginning was supposed to be increasingly irrelevant in the AI world dominated by GPU clusters. That narrative is now being revised. Because of agent paradigm we just discussed, the orchestration layer, the code that manages multi-step workflows, tool calls, memory state, and API integrations, is CPU native work. You cannot economically run complex agentic workflows on GPU clusters alone. The GPU excels at massive parallelism, the CPU excels at sequential logic and general purpose computation. As agents become more sophisticated, demand for CPU capacity in AI infrastructure is growing. Second surprise, domestic chip manufacturing. For years, the dominant narrative in semiconductors was that manufacturing had moved offshore permanently. TSMC in Taiwan, Samsung in Korea, and that was fine until it wasn't. Intel, a company that many observers had declared a fading giant, is actually in a uniquely strategic position. It is the only major American company that can both design and manufacture leading edge chips at scale. In an era where US China tensions are reshaping the semiconductor industry, and where the CHIPS Act has committed $52 billion to domestic manufacturing, that matters enormously. And the broader lesson from history, Nokia had the best mobile hardware in 2006 and still lost. Sun Microsystem had the best servers and lost to AWS. Infrastructure dominance doesn't guarantee stack dominance. Strategic investment landscape, where structural tailwinds are strongest and where disruption risk is high. Let me synthesize everything we have covered into a practical framework for thinking about where value is likely to be created versus destroyed over the next several years. On the left, structural tailwinds. These are areas where the fundamental dynamics we have discussed, the compute growth, the energy demand, the agent transition, the supply chain pressures create durable long-term demand. Foundational compute infrastructure, the chips, the accelerators, the systems that actually run AI. Despite the commoditization pressure over time, the absolute demand here continues to grow, power distribution and battery technology. Every gigawatt of AI compute needs reliable power. The infrastructure to deliver it, grid upgrades, energy storage, power distribution system is a multi-decade build-out. Material science and transistor research. The physical limits of silicon are approaching, the organizations working on what comes next. New materials, new transistor architectures are doing foundation work with enormous downstream value. Data center real estate, physical land, cooling system facilities, AI needs places to live. High bandwidth networking, moving data between compute nodes at the speeds required for a large data scale AI is a solved problem that keeps needing to be solved again and again at larger scale every few years. Nuclear energy, the air industry is effectively betting on nuclear as a long-term power solution. And CPU manufacturers, as we just discussed, benefiting from the agent transition. On the right, high disruption risk, model wrappers, software that simply call an AI API and resells the output without adding deep technical value are vulnerable. Any application that doesn't have a genuine technical moat will face competitive pressure from the models themselves as they become more capable and directly accessible. 7 things to remember. We have covered a lot of ground. Let me distill it into 7 key takeaways that I want you to walk out of here with. 1. Compute is capital. For frontier AI labs, compute capacity is the primary asset. Revenue follows compute, not the other way around. No ceiling has been observed. 2. Inference dominates. The old assumption that AI compute is mostly about training is wrong. Over 80% of the compute footprint will be inference, running the model, reasoning, generating synthetic data, powering agent loops. 3. The agents change the architecture. The shift from chatbots to agents isn't just a feature improvement, it requires fundamentally different infrastructure, heterogeneous hardware, and new software architectures. 4. Power is the binding constraint, not chips, not talent, but power. The gigawatt problem is real, and it's reshaping energy policy, driving nuclear investment, and decoupling data centers from public grids. 5. Supply chains are dangerously thin. The entire AI revolution runs through a handful of companies and one machine made by one company that cannot be quickly replicated. 6. AI is designing its own successors. Recursive design loops are compressing the chip design cycle from years to potentially months. The technology is participating in its own acceleration. 7. Value migrates up the stack. Infrastructure captures value first, then platforms, then applications. We are early in that migration. The question is whether you position yourself where value is going, not where it is today. The AI supercycle is not a software story. I want to say that one more time because I think it's the thing that most people get wrong about what's happening right now. The AI supercycle is not a software story. The coverage tends to focus on models, how clever they are, what they can write, what they can create, and that's genuinely interesting. But it is the surface. The underlying story is about the physical infrastructure, about gigawatts of power and the grids that carry them, about fabrication plants that cost tens of billions of dollars and takes years to build, about a single Dutch company's monopoly on a machine that the entire global chip supply chain depends on, about transit corridors and trade policy and the locations of TSMC factories relative to potential military conflict zones. The companies and nations that master the compute layer, that secure the chips, the power, the supply chains, will define the economic landscape of the next decade, and in some cases, the political landscapes too. This is why the language around AI has shifted from technology to infrastructure. This is why AI is being discussed in the same conversations as semiconductor policy, energy independence, and national security. The stakes are genuinely that high. We are, I believe, at an inflection point analogous to the early days of electrification, the moment when a new form of power became so fundamental to economic activity that controlling it meant controlling the future. The race ahead is not just technological, it is geological, it's electrical, and it's geopolitical. Thank you.